Good. So what does the word poly mean? Many, multi, and what does the word gon mean? Gone. Side, yeah. So literally the word polygon means just many sides. So today we're going over various polygons that you're going to come across. Now, I actually love going over polygons because a lot of the properties of polygons are patterns. So if you understand the core concept of polygons, you'll understand everything about polygons because everything is formulated from a pattern here. So we're going to fill out this chart together. First, we're going to name these polygons. So what is that very first shape, do you think? Oh my gosh, it's a triangle. Good, you got it.
That was so hard.
Right? It's so difficult. And it has how many sides? 3. What about that next shape? What is that?
Rectangle.
Yes, but more specifically, it's a quadrilateral. Or I guess less specifically, it's a quadrilateral. All quadrilaterals have 4 sides. What about the next shape, that 5-sided shape? It is a pentagon. Good. And then?
Hexagon.
Yes, hexagon is 6 sides. Wow, they are loud over there. I'm going to shut the door. And what about a 7-sided shape? This one's tricky. What is it?
Hexagon.
Heptagon.
Yeah.
I know. Yeah, septagon, heptagon. It gets really cloudy between those two. What happened to Lauren?
I used to get those 2 shapes.
Then, what about this? Octagon. Good. 9? Who knows a 9? What is it?
Nonagon.
Nonagon. Nonagon. And lastly, decagon. Decagon. Now, we're going to go over the next two, 11 and 12. Not really because you need to know 11, but 12 is used a lot. So 11, and I'm going to misspell this. I know. Maybe I should look at it. 11, who knows what an 11-sided shape is called? Technically, and this is the hardest one, technically, 11-sided shape is a decagon.
How does it look like?
And a 12-sided shape, it looks almost like a circle, right? It has 11 sides. And 12-sided shape is a dodecagon.
Like those? Like
Dodecagon. Ah, interesting. Okay, I gave you the wrong. Yeah. So I looked on previous notes from a student, and she had written down Nenacagon. I don't know where the heck she got that from. This is a hendecagon. That makes a lot more sense. Hendecagon. And a lot easier to spell, too. Hendecagon. And say. Okay, so now we are going to find the number of triangles that we can create inside of each one of these shapes. So the rules for creating these triangles are they are created by drawing in the diagonals, and the diagonals always need to start at one vertex. So they always start at one vertex, and you guys know that a diagonal goes from a vertex to another vertex. So if I'm trying to create multiple triangles inside of a triangle, is it possible? So remember, to create a triangle inside of a triangle, to create a triangle inside of a polygon, you have to go from one vertex to another vertex. What happens when I go from one vertex to another vertex on a triangle? Are you creating another triangle inside of that triangle? No, right? You're just following the sides. So how many triangles are inside of a triangle? One. Then, moving on, I'm going to create a diagonal inside of this quadrilateral, starting at one vertex and going to another vertex. So how many triangles did I create here? Two. And then, remember, you always have to start at the same vertex. So I'm going to create my diagonals, starting at the same vertex, going from vertex to vertex. How many triangles did I now create? 3. Do you think you got it, or do you want me to do one more? One more, okay. So pick any vertex to start at, it doesn't matter which, and draw a diagonal from vertex to vertex, vertex to vertex, and vertex to vertex. How many triangles did I create?
4.
All right, I want you guys to finish up this column and also make sure you're drawing in those diagonals. I want to see them. How many triangles did you find inside of a heptagon MS? In a heptagon, sorry, a 7-sided shape.
5.
Good. So we draw in our diagonals, diagonal, and 5 triangles are created. Then octagon, how many did you find inside of an octagon, Gwen?
6.
Good. What about a nonagon? Liv?
7.
And morning, what'd you get for decagon?
8.
8. Wonderful. Now, what pattern do you see when creating these triangles? Yes, okay. So most importantly, as we're creating this chart, let's also at the top create expressions, variable expressions that would represent each one of these columns. So and does anyone know what variable normally represents number of sides?
S.
Not S.
N.
N. Yes.
Oh, no.
Wow.
Bad.
Yes. So N is number of sides. So if N is our number of sides, what expression could represent the number of triangles?
N
N -2. Perfect. Now, if you have a highlighter or something, these expressions that we're writing at the top are very important. So make sure that they're clearly marked. Okay. So does anyone have a guess as to why I made you find the number of triangles inside of a polygon? Yeah, but I mean, I could just randomly ask you, okay, how many squares fit in each side inside of each one of these? There's a specific reason why I asked you to find the triangles. Why do you think that is? Oh, we can do it. Use our brains. What's special about triangles? They have 3 sides, okay. What do we know special about them? They make up what? Yeah,
Are you asking about like angles?
maybe.
So like triangles are
Oh my God. For sure, always. What do the angles inside of a triangle add up to? 180 degrees. So, if we know that a triangle sums to 180 degrees, can't we know from the number of triangles what all polygons sum to?
Yeah.
And how would we do that? Oh my gosh, we multiply 180 times the number of triangles, and boom, we have the sum of the interior angles. So, triangle is easy. We know. What does it sum to? 180. Beautiful. Now next, how would I find the sum of the interiors on a quadrilateral?
360.
And how'd you get 360?
By multiplying 180 times 4.
Beautiful. The number of sides times 180 gives us 360. What about pentagon? What would we multiply here? 3 times 180. And we get? All right, you guys finish up this column. Emma P., what did you get for the sum of the interiors on a hexagon? Yes, 720. Now, I highly recommend that you're writing down how you get these numbers, because later on you want to be able to look back and say, oh, that's right, that's how we found the sum of the interiors, right? Then, what about heptagon? What was the sum there, Robert? 900, good. Next, octagon. Julie, oh. Abby Hill. Wonderful. And then, Vu, what'd you get for nonagon? A nonagon?
Oh, 1,060. Oh, 1,260.
There we go. And then decagon. What you get, Liam?
1,440.
Yes. All right. So now, let's quickly go over what a regular polygon is. So, oh crap, no, wait. Who thinks that they have an idea for what the expression to find the sum of the interiors would be? Sam, yeah?
Never mind.
Oh, just,
The sum of interior angles?
yes, the expression for it.
180 times in parentheses n minus 2.
Beautiful, yes. 180 times n minus 2. Beautiful. So then, next column, we're finding the measure of one interior angle only when it's a regular polygon. So at the bottom here, let's go over what a regular polygon is. You should. Unless you write in like size 24 font.
So, I mean, like, were we supposed to, like, find the measure or
No, we're not finding the measures for those. No.
Oh.
Oh, were you? Oh, you don't have to. No. Okay. So, what do you think a regular polygon is? Oh, you guys are just so bright. A regular polygon is when all sides and angles are congruent. So, what would an example of a regular polygon be for a triangle? An equilateral triangle. Good. So, a regular polygon is when all sides and angles are congruent. So because we know in a regular polygon all angles are equal, how could we find the measure of one angle in a triangle? And how'd you get that? Yes, you take 180, the sum of the interiors, and divide it by what? The number of sides. Sides. So we get 60 degrees. Then, what do you think we do for quadrilaterals? 360 divided by what? 4. Good. which is 90. Do you understand what's happening? All right, you guys go ahead and finish the column. What did we get for the measure of one angle inside of a pentagon?
108.
Good. Oh, sorry, I meant to call out Serena. What'd you get?
108.
Wonderful. Then, what did we get for hexagon one angle tests?
Hexagon?
Yes.
120.
Good. Then heptagon. What did we get, Olivia?
Hexagon. 128.5.
Yes. 128.57 degrees. Then heptagon. What'd you get, Shira?
135. Wait, octagon or? Yeah.
You got it. Then nonagon. What'd you get, Bargov?
140.
Wonderful. And lastly, decagon, Holton.
144.
Yes. Any questions on how we got those angles? Does anyone think that they know what the expression would be for this column?
So divided by n.
180 times n minus 2 divided by
N.
Yes. 180 times n minus 2 divided by n. This is the measure of one interior angle in a regular polygon. Must be regular for you to do this. If it's not regular, you can't use this method, right? Because not all the angles are the same. So clearly, you can't just divide by the number of sides. Okay, the next one is the most complex. Very tricky, this one. What I want you to do is draw a triangle with all of its exterior angles. And if you remember from last unit, a triangle's exterior angle is created by extending the side outward past the edge of the triangle. So here I have a triangle with its 3 exterior angles. So say this was an equilateral triangle, right? A regular polygon. What is the measure of, say, this angle right here?
60.
Good, 60. So what is the what is the exterior angle right next to it equal to then? 120, right? What about this exterior angle if that angle right next to it is 60? It's also 120. And the last exterior angle, what do you think that is? What do those add up to? 360. And guess what? No matter if it's a regular polygon or not, every single polygon's exterior angles will always add up to be 360. All of them.
You said it was tricky.
Right? I was being sarcastic. It's the trickiest of them all for sure. So, say that we do have a regular polygon. How would we find the measure of one of the exterior angles? 360 divided by the number of sides. So here, 360 divided by the number of sides is 3 is 120. Then 360 divided by what for a quadrilateral, you think? 4 is 90. Okay, you guys finish up the column. What did you get for What is this third one? A pentagon. Haley?
72.
What'd you get for the next one, Sam? For a hexagon.
60.
What you get for heptagon, Sean? Heptagon? 7-sided?
52. Oh, 72.
No, not 72.
Which one again?
Heptagon, 7-sided shape.
Yeah, isn't it 51.4?
Yes. Then what you get for octagon, Emma B? Yes. Then nonagon, Lauren. Nope. Ian. 40. And last but not least, decagon, Jolie.
36.
Wonderful. Any questions on anything on this chart? All right, what I want you to do, and I haven't given you your notebooks back, I'm gonna grade them while you guys are practicing, but I want you to fold these in half, and we're gonna do 2 problems on the front blank side. On this problem, yes, you do need to know the sum of the interior angles. Now, of course, you can look at the handy chart we just made. However, on a test, do you think I'm going to give you the chart? No, I'm not. Instead, how can you find the sum of the interiors without looking at the chart? What do? You can either draw the triangles inside the shape or remember what? N minus 2 times 180, right? The number of triangle, or the number of sides minus 2 times 180. So the number of sides here is 7, right? So 7 minus 2 is 5 times 180 gives us what? Yes. No, just solve for x. So now you know that all of these angles add up to what? 900. Okay, you guys go ahead and solve for x now. All right, what did you guys get for x? Let's see, should I call on the one of the 6 left? I think I should. Steven, what did you get? 49.58 what? What? Degrees. Any questions on that problem? All right. Now on to number 2.
How many are there?
Just 2. And I would like for you to solve for x. What did you get for x, Cooper? You got 62, and how'd you get that? Shh. Hey!
Add 30, 42, and 40.
Beautiful. Yes. So we end up, when we add up all the angles, we get 4x plus 112 equals, and exterior angles always add up to 360, and then we solve for x, and we get 62 degrees. Any questions on either one of these problems? All right.
That thing, because it already has those things on the 3x.
Hmm?
We don't need to put the
Like,
degrees.
yeah, you don't have to put the degrees.
That means that we could get our point back.
Yeah.
So I know what you're saying. Here it's a little bit ambiguous. Ambiguous. It's a little ambiguous whether or not you need to put the degree symbol, but I would always just err on the side of caution and put the unit.
Oh, you put it.
All right. Now, before we start the practice, which we're not going to have too much time in the practice, that's okay. Before we start, there are a few things I would like to go over, which you guys probably already intrinsically know about polygons, but what are some things that make a polygon? There are 3 specific things that every polygon must uphold to be a polygon. Has to be a closed figure. Meaning, this is not a polygon. Not a polygon. What else do you think? What else does a polygon have to be? Or can it not have? Yeah, it has to be a shape. It cannot have no curved edges. So this is not a polygon. And the last one is kind of hard to think about. I didn't have any class figure this one out. But you cannot have overlapping sides. Whoops. So this entire shape is not a polygon. Yes, if we split it into 2, it would be 2 polygons, right? A triangle and a triangle. But in and of itself is not a polygon. And then just very quickly, I want to go over the differences between concave and convex. What does concave sound like? A cave, right? So a concave polygon is going to go inward like a cave. The real definition is a concave polygon has a diagonal outside of the shape. That's what really makes it concave. If we go from vertex to vertex, the diagonal is outside. Remember, diagonals going from vertex to vertex, right? So that dotted line I drew is technically a diagonal. However, it's outside of the shape, so it is a concave shape. And convex is literally anything that is not concave, with all the diagonals on the inside. Any questions? This is pretty straightforward, right?